to the cloud. So the directions say solve each on 0 to 2 pi. So looking for any solution that exists on the interval of 0 to 2 pi of this equation, 2 sine theta plus 5 equals 4 sine theta plus 6. Right? This is not verifying a trig identity. It's not the idea where we want to get a balance where the left side is equal to the right side. I want to isolate the value of theta and get an answer or multiple answers. All right. So the one thing that we want to keep in mind, because you'll see some examples where it's exclusively in terms of sine, exclusively in terms of cosine, and then you'll see an example where it's a mixed situation. Sine of theta and cosine of theta are not the same variable. They'll say are different variables. And I'm going to put that in quotes. All right. And that's because, oh, that's a little thicker than I wanted it to be. The theta itself is the same. It's just when you take a function of a variable, the function of theta, it produces a different ratio. And those ratios are not the kind that can be combined like two like variables can be combined. Right? So I can't just add a sine and a cosine and expect to get something meaningful. All right, but I can add a sine and a sine because those are like terms. Okay. So when I go to solve number 1, I want to get all of my sine thetas on the same side of the equation. Doesn't matter what side that is because it's an equation. You know, it's commutative. So I'm going to subtract a 4 sine theta from the right over to the left. So I'm going to be left with a -2 sine theta because I'm treating sine theta as if it's a variable. Since we have like terms, the sine of theta and the sine of theta, all I'm going to do is subtract the coefficients associated with those variables. I still have the +5, and I still have the 6. So I'm going to subtract off the 5. I'm going to subtract off the 5 from both sides. And I'm going to be left with -2 sine theta is equal to 1. If I want to get sine of theta alone, I would divide both sides by -2. And I'd be left with sine of theta is equal to -1/2. All right. What I want is theta over the interval of 0 to 2 pi. All right. So I think I did this last class where I accidentally copied and pasted an entire unit circle. Oh yeah, there it is. I'm going to steal that, bring it over here. Teensy tiny. But then I'm going to zoom in a lot because when we talk about sine of theta, we're talking about the y value for any coordinate on the unit circle. All right, so if I'm telling you that the y value for a y value for a coordinate on the unit circle is -1/2, then all I'd have to do is go into my unit circle and look for any instance in which the y value is equal to a -1/2. Right? And before I forget, copy that. So that would be this one, which corresponds with a radian measure of 7 pi over 6. And that would be this one, which corresponds with a radian measure of 11 pi over 6. Right? They said the domain is 0 to 2 pi. So we don't want to go any further beyond that. You know, like I don't want to try to get coterminal angles that are beyond 2 pi radians or 360 degrees. So my theta here is going to be 7 pi over 6 and 11 pi over 6, because those are the only instances in one turn of the unit circle where the sign value is -1/2. Number two gets a little jazzier. So we have cosine squared theta is equal to 5 plus 8 cosine theta. Now this one, if we're treating sines and cosines as different variables from each other, we're treating them, oh, thanks, Joel, I'll get you for attendance in a minute. We're treating them as variables in and of themselves. So we got to kind of sort of think of this as x squared. I know that looks weird, but it's like quote unquote x squared is equal to 5 plus 8 quote unquote x. All right. So, because it's not really x. I mean, there's a certain circumstance in which it's equal to x, and that is on the circumference of a circle with a radius of 1, but it's not always equal to x. So we don't want to fall in love with that idea. But we could say that we have a variable squared is equal to 5 plus 8 times another variable. That's quadratic. And that's got a quadratic structure. And when you solve a quadratic equation, you get everything over to the same side. You factor or use quadratic formula or completing the square, which we'll talk about a little bit later in this unit, and solve, right? So subtract the 8 cosine theta. I'll do it all in one shot. You know what? I won't do it all in one shot. I'll do it in separate shots here. All right, so cosine squared theta minus 8 cosine theta, those aren't like terms, because just like you can't add an x squared and an x because one's a power of 2 and one's a power of 1. Those aren't like terms. They don't have the same power. You can't do the same thing with trig functions. All right, so this is equal to 5, and then I would subtract the 5 from both sides. In which case I would get cosine squared theta minus 8 cosine theta minus 5 is equal to 0. All right. Now, if this were, so think x squared minus 8x minus 5 equals 0. If this were that, what would you do? You'd probably use the quadratic formula to solve it. All right. So, I mean, and that's only because you're looking at something that isn't factorable. You got a 5, the product values that give you a 5 would be 5 and 1. That's never going to get you to an 8, right? So if this were x squared minus 8x minus 5 equals 0, then the quadratic formula, if you remember, would be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But it's not x, right? The variable is not x, it's actually cosine. So instead of x equals, we would say cosine of theta equals. But the coefficients are all still structured the same way. So as long as you can pull out your coefficients from the quadratic, you'll have your a, b, and c values, and you'll be able to evaluate this. All right, but in a couple minutes, I'm going to show you the tech assignment, which is going to show you how you can handle this using Desmos. All right, so it's an alternative approach. So the leading coefficient here is a 1. We have a negative 8, and then we have a negative 5. Poor quality negative 5. I'm going to clean that up. All right, these would be our a, b, and c values.
Yeah.
Oh,
I'm in class.
me too.
Don't listen to that.
So A, B, and C are 1, -8, and -5. So I could pop that into my quadratic formula. Okay, it's just a question. I'm going to shrink it up a little bit just so I can fit it below. So negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so negative, the b value is -8, plus or minus the square root of b squared, so -8 squared minus 4 times 1 times -5, all over 2 times 1. All right, so we'll have to crunch these numbers a little bit, but whatever we get as a result is going to be equivalent to cosine of theta for this equation. All right, so I'm just going to pop it into Desmos. Negative, I'll just type it in as I see it. Negative parentheses -8. I know that's redundant, but I'm going to put it in anyway. Minus radical. So I'll do the minus first and the plus second. Parentheses -8. Close it up, square it. Minus 4 times 1 times -5 all over 2 times 1. So we get that funky decimal. It's not the nicest looking decimal in the world, but it gets the job done. All right, I'm going to hit that little gear icon and duplicate and make the minus over here. I'll get to where I'm talking about in a second. The minus right in front of that radical, I'm going to make that a plus, and that gives us a different value. All right, so we see we have 2 results of the quadratic formula. Bring this back a little bit. So I can now say, as a result, that cosine of theta is equal to 2 possibilities. One of them is about -0.5826. And then we could say, or cosine theta is equal to 8.5826. All right. So now we have something to work with here. I mean, it ain't pretty, but it's trig. It's not always going to be pretty. So then what we would do, and we talked about this last time, is if we want to find the result for theta when it's contained within a trig function, we find the inverse of both sides of that trig equation. All right, so actually let me move my arrow a little bit and do it like this. So this would be saying the arc cosine or the inverse cosine, whichever notation you prefer. I'd say arc cosine of, and then we would do that for the left side and for the right side. Okay, so arc cosine of cosine of theta is going to be equal to arc cosine of -0.5826. And just to address a question that I probably would be wondering at this point, why aren't we using the unit circle for this question where we did for the last one? Because the cosine values, the 0.5826 and the 8.5826, they're not clean, nice unit circle ratios like radical 2/2 or radical 3/2 or something like that. All right, they're these. All right, so they're not friendly, so we go to the calculator for it. All right, so we get theta is equal to, and then we would just have to find the arc cosine of that number. All right, so then you could type in arc cosine. Oops. All right, Desmos recognizes that. and then type in the decimal. At which point you would get 2.193 or 1927 as well, right? Radians. All right, but we got to be careful about that answer. I'll explain why in a minute. But I also want to evaluate the arc cosine of the other one, this guy over here. All right, so I would have to do, I'm going to do a little shrinky dinky now. All right, so in this one, I'm going to put the 8.5826. All right, so in Desmos, I would check that out. And you see that that gives us undefined. And that's because trig, not all trig functions, but the sine and cosine ratios can only exist between -1 and 1. So this one wouldn't give us a solution, which is good because we had our hands full with the other piece to begin with. But it's meaningful. You know, it's a little, if you're not as comfortable with trig ratios, it's a little surprising, right? But if you look at the cosine ratio or cosine graph, I'll just type in y equals cosine. I'll just use an x. See that the highest it ever goes is 1, and the lowest it ever goes is -1. What this is saying is that there's a point somewhere up here around 10. My screen froze, but that stinks. Well, I don't know what to do now. I'll stop the share and I'll start it again, I guess. That's one thing I can do. Still doesn't want to connect. Resume recording. Okay. So yeah, what I was saying is that if you have a graph that only goes as high as a +1, and yet they're telling us to bring it up as high as 8.5, you know, I'll plot 8.5. 8.5826, be more precise. Anyway, they're saying that it's got to reach up this high, up as high as that purple graph. The highest it'll ever go is 1 on the green graph. So it's a contradiction. It wouldn't play out that way. All right, but that's going to kind of bring me to how we would approach this for a graphical solution. So let's say, for example, we wanted to figure out this one without using the arc function and just go straight to the answer, right? And I said we had to be cautious about this answer because there could be actually multiple answers that we're missing out on. This approach that I'm about to show you is going to kind of steer you in that direction. So let me get rid of some of this fluff here. What you would do is you would actually do what I just did here. You would let y equal one side of the equation and y equal the other side of the equation and see where they cross. All right. So the other side of the equation is negative 0.5 whatever, but I also want to restrict it so that it only goes to the appropriate values within the domain, right? So they told me, it's a way back here, but they said solve each on 0 to 2 pi, right? So that's what I would actually have to keep in mind. Let me zoom out before I zoom back in. But only on 0 to 2 pi. So in Desmos, I would actually write 0 less than or equal to whatever variable I'm using, x in this case, 2 pi. That's what I'm going to put in here right after my cosine function. So that I only get the relevant part of the graph. Now, if I tap on those intersections, I'll bring it in a little closer. Tap on those intersections. You see that there's multiple intersections. I have 2 answers here. And I'll show you where the other one comes from in a second. But we have theta is equal to 2.1927. They say 2.193. It's the same thing because it rounds to the same way, same value. But theta would also be equal to 4.09 radians. All right. So I have to show you where that would come from. So let me just draw a quick sketch. So ASTC, remember that means that all trig functions are positive in the first quadrant. Only the sine related ones are positive in the second quadrant. Only tangent are in the third quadrant, and the cosine related functions are positive in the fourth quadrant. All right. When we solved this and came up with, sorry, 2.1927, what we did again is we used the arc cosine function, arc cosine, and I typed in negative 0.582826. And it gave me that value in radian form. If I change it over into degree mode by hitting that little wrench, it tells me that that's about 125 degrees. So I'm just going to go with about 125.6 degrees. All right. So if I'm plotting that, that's going to put me about right here. Draw it straightish. So this is approximately 125.6 degrees. All right. So then what I'd be looking at is we have a negative value for cosine. A negative value for cosine can exist in multiple places within one turn around the circle, the unit circle. So I'd want to be thinking about where else could cosine be negative, because this is a negative ratio. All right, cosine is negative in the second quadrant, but also in the third quadrant. So that would actually indirectly give me another angle in the third quadrant consistent with that 125 degree angle. All right, it would have the same reference angle. Right, it would have the exact same reference angle, but we don't actually have to work with that because since it's symmetrical, if this is going 125 degrees in the counterclockwise direction, then this one would be going 125 degrees approximately in the clockwise direction. So if I wanted to figure out what this true angle was, I could do 360 minus that 125.6, right? So to find this missing angle here, this whole oh yeah, that looks great. This whole shebang, let me just do it like this. I'm going to do 360 minus 125.6. which is about 234.4. But then I would have to convert that over into radian measure, right? So alternatively, what you might say is, well, we know that this 125.6 degrees was about 2.193 radians, right? So this is about let me make it a little thinner. 2.193 radians. If over here we're saying take 360 and subtract from it the angular measure, why not take 2 pi and subtract from it the radian measure? So 2 pi minus 2.193, and from there you get your approximate 4.09 radians. Right, which is what we got using the calculator shortcut. All right, so there's definitely a lot of stuff going on with this type of problem, but especially as you look at it, I mean, with the quadratic component, the unit circle part of it, it can be a lot. But if you look at it with the graphing calculator, it becomes a whole lot easier. It all depends on how you need to represent your final answers. All right, so let me shift over and show you how you can do this. Well, let me just show you the tech assignment so that, one, I don't have to worry about this glitching out on me anymore. And two, you're not just restricted to the easier cases, because number one wasn't that bad. And by the way, if I ever ask you to do this by hand, I want to be clear. Any question that I would ask you to do by hand would be of the difficulty level of number one. All right. If I ever ask you to do something like number two on a test, it's going to be with the stipulation that you could do it using the Desmos approach, or you could do it by hand, whichever you prefer. Most people, I think, are going to prefer the Desmos approach. Right. So just wanted to be clear about that. Clear being the word of the day. Clear. C-L-E-A-R. Clear is the word of the day. All right, so I'm putting stars on the remaining problems here. And then we're going to switch over to the tech assignment. Believe it or not, there's only like one more topic in Trig, and then that's it. For the Trig portion of the course, we just have to touch on conic sections, and then that's it. So we are in the home stretch. But this tech assignment is probably one of the more important ones that that I have for you, or it is the most important one. I can say that without a doubt. Stop this. All right, so under tech assignments, the third one, let's see, item is hidden for students, so let's make that available. All right, so it should be available now. I'm going to click on the assignment. Everything on this page is pretty straightforward, but there is one thing here, a Desmos trig equation randomizer, which you'll click on, and you'll see that there is a randomizer. All right, so, and I'll show you what you're going to do with that in a minute. All right, so we go back to the assignment, actually open it. I'll do the PDF version. All right, so I gave you a guided example here. It walks you through it step by step. I don't think that's probably the best idea to just rehash the same guided example. It's kind of a waste. You have a set of problems that you're going to do, and then the fifth problem is going to be the randomized problem. All right, so it says use the equation generator in the link attached on Blackboard to create a unique equation to solve using the Desmos technique above, which I'm going to walk you through now anyway. You can hit generate new problem as many times as you want, because if you look at one and be like, I'm not going to be able to do this one, then don't do that one. Do something simpler. All right. But let me open a Desmos calculator and show you what this is all about. All right. So what you're going to do is you're going to solve the given equation, but in doing so, you're going to have to type in multiple items into your Desmos. So you're going to want to have an organizational strategy. Some people like to use folders for stuff like this, and I'll show you what I mean by that in a sec. But yeah, an organizational strategy is going to be the best way to go, and just to keep things clear. Now you'll notice that there's a change in domain from numbers 1 through 3 and then on to 4. What people have done in the past with this is they create a different Desmos for number 4, because one Desmos should be in radian mode and the other should be in degree mode. All right, I leave that up to you how you want to organize that, but that was what a lot of people thought were the easiest thing to do in the past. All right, so what you would do, I'm going to just sign in with Google if it'll let me. Yep, continue with the activity. Click generate new problem. If you don't like the one that you see, just generate. Like, keep going until you find something that you like. Whatever you think. Like, this one looks all right. You know, and I apologize for the changes in format. I'm still kind of working on the, you know, keeping this as clean as possible, but I'm going to snip this or screen grab it, however you do that. And I'm going to actually put this into the Desmos just so I don't lose it. Right. The way that you do that, if you're doing it on a Mac, it's easy enough because you just import the file. Yeah, but if you're doing it on a PC, you have to do like with the snipping tool, you have to do that extra step of saving it to a file. You know, it's not terrible. It's just an extra step. Right. So I'm just going to bring that in. If you need to add an item, bring in an image, do it this way. Click on the plus and then click on image, and then you should have it wherever you saved it. And then I just bring it in. If you click on it, you see the little dots. The middle one allows you to relocate the item. You see it changes the coordinates of the center as I move it in the editor on the left-hand side. You see that the coordinates of the center are changing. But I could also shrink it down and change its location. I just want to kind of have it there, but out of the way. Right. And if you click on this, it'll go away completely. So that's something. You know, but I just want to have it there, but you know, for reference, just so it's available, but it's not going to get in the way. All right. And in fact, I would put this in a folder, and I'd call that question 5. All right. The left side of this equation goes in as y equals 0. All right. Hit enter. The right-hand side goes in as its own equation. So y equals cosine, open parentheses, 7x squared, that looks fun, minus 5 squared. All right. I'm sorry, cubed. All right. So this is kind of a mess. You see the domain here only goes from negative pi to pi. So what I would do is I would restrict this, open the squiggly brackets, negative pi, less than or equal. On the keyboard shortcut for less than or equal, less than followed by equal. Surprise, surprise. Less than followed by equal, positive pi. And you see it creates a restriction. Now, maybe I want to have these a little closer. I don't know. But this is my graph, and each one of these intercepts represents a solution. All right. So sometimes it isn't until after you do this work where you realize, okay, maybe I don't want this equation, but I'm, you know, in for a penny here. So I don't like having the background grid. So I'm going to hit that little wrench and turn off the grid. I think that looks a little bit better, right? I don't need it to go down and as low as -6 and as high as +6. So on my y-axis, I'll make it go really -1.5 would be enough. -1 will even do it, but I'm going to put -1.5 and then +1.5. And then you know, with my zooming, it kind of took me out of the domain a little bit. So I'd bring it to negative pi to pi, or bring it from negative pi to pi, just so I get a good look, and then I'd zoom out from there. Right. So every one of these little intersections here represents a solution. Right. So we need all of those, which is really probably the most aggravating part of this. But what I would recommend you do, if you can't, because what I'm trying to do here, which would be ideal, is get all of these intersections to show up on the screen without overlapping each other. But you see, it gets a little crazy after a while. And if it won't show up the right way, then you might have to do something else. But this looks all right, at least for half of it. So what I would do is do this, and then take a quick screen grab of this, and then, you know, it's kind of like an app within an app. You know, it's a little inception going on here. If you take a screen grab of this and then paste that in there, you'll have your solution. You know, like you won't have to retype it all. Right? If not, it's like, all right, well, get to typing, because once you click, they all go away. So it's like, all right, what's my first one? You type a note here saying solutions. Negative 3.0767. So I'd say negative 3.7. So in this case, it's x. So x is equal to negative 3.0767, comma. And then you go for the next one, negative 3.0028. And then you go down the line until you got to the other side. Now it is symmetrical, so you could take advantage of pluses and minuses, but that could be a little much, right? So you want to try to do it efficiently, but also correctly. All right. Now, what that, you know, I would take a look at this, and even though I might have done the work, I'd look at this and say, well, I don't know if I like this problem. So maybe I go back to my randomizer and generate something different and see what's going on. Maybe those high powers are tricky or too tricky. So maybe you try something different. All right. But the idea is you come up with something that you can produce a solution for. And again, that solution would be very simple in the sense that I'm not really asking you to do much beyond graph the two parts, find where they cross, and then indicate what those solutions are. It can be a little tedious, very tedious, I should say, to indicate what those solutions are, but it is doable, and it's easily done. All right. But I can do just so I can show you an easier one. Let me close this folder. See, if I close the folder and click on the folder itself, everything that's in that folder goes away. So that's what I meant before when I said about organizing your work. So let's say I wanted to do number three from the notes. All right. This one was -3 sine squared theta. So 3 sine squared theta, but we're going to use an x, minus cosine x. All right, that was the left side, so I make that y equals. All right, the right side is just a 1, so y equals 1. All right, but it's only over the interval of 0 to 2 pi. All right. So if I look at this one isn't really that bad, because when I click on my intersections, I have my 3 solutions here. One of them is actually in terms of pi, which is really nice. All right. So like some could be pretty easy, you know, 0.841, 5.442. And then there was a pi mixed in the middle, so I'll just tuck that in there. When you do it as a note pi doesn't come up as the symbol. It just comes up when you write pi, it just comes up as pi, and that's fine. You can write that as pi. All right, but this would be a nice easy one, you know. And so if I wanted to, let's say that this were a question on the tech assignment, it's not, but I could say that this is page 54 in the notes, number 3. All right, so I took the left side, I made it an equation. I took the right side, I made it an equation. And I indicated my solutions. And that's it, it's all tucked away in a folder. So now if I click this one off, but click this one back on, you see I have everything that comes along with each of those equations, each of those problems. Those are the only things that come up. All right, so it's a nice organizational strategy. That's what I was saying when it comes to the tech assignment. You know, these are going to be pretty easy. This one you might want to create a new Desmos for, just because it's in 0 to 360, unless I'll allow for this. Convert this over to radian form, which shouldn't be too difficult, in which case you could do all of them on the same one. But you'd have to put your answers for number 4, your answers have to be in degree form. So you could do all the work in radians, but your answer has to be in degrees. All right. But if you do it efficiently, you should be able to get everything all into one Desmos. All right. So let me stop the recording.